Good afternoon, everyone. My name is Shyam, and I'll be presenting our work on K3, the language we've been working on to build efficient, multi-platform, domain-specific runtimes. This is work done with my colleague Zach Palmer and my advisor Yannick Ahmad at the Data Management Systems Lab at Johns Hopkins University. This is a work in progress, so we appreciate your comments and thoughts on what I'm going to be presenting today. A rough outline of this talk, I'll first give a high-level view of why we're in this space, why we're developing this language, why we're developing yet another systems language, and the problems that we wanted to solve. I'll then move on to some language design issues, and the decisions we've made in hopefully accomplishing some of these goals. I'll then discuss our annotation model, which is a large part of our design space for that. And I'll close with some details about where we are with the project and where we want to go from there. So let's start with some terminology, because every word I'm using in this presentation is overloaded. So what are domain-specific runtimes? Well, runtimes are systems that underlie an application's execution. So it makes decisions about the execution, such as how the data is stored, how it's moved, how it's accessed, how concurrent execution is coordinated, and so on. General purpose runtimes like the JVM and CLR cater to a wide range of programs. Domain-specific runtimes, on the other hand, focus on a narrower range of programs and use the information they know about their domain to make better choices about the implementation and provide further optimizations. For example, Hadoop is a domain-specific runtime. It focuses just on MapReduce programs and provides services like data partitioning and job control and so on. Pre-Go is similarly a domain-specific runtime for a specific type of graph processing algorithms. And Link lets you express data queries in a generic SQL-like syntax, and then lets you choose separately what runtime you'd like to fulfill this functionality. Obviously, domain-specific runtimes are useful because they're more specialized in their particular class of programs. The problem, of course, is what happens when your application is not in a domain that has a good runtime associated with it. After all, not every program is a MapReduce program. This issue is faced by a lot of people who have a specific task and therefore have to build a specific data processing pipeline in order to accomplish that task. In this case, you have a few options. You can alter your application's requirements so that it is fitting into an existing domain, which is essentially similar to hammering your program into MapReduce. You can compose multiple runtimes together so that subparts of your application are serviced by specific runtimes. You then have to glue these components together using code that you have to write and maintain. Otherwise, you can write your own runtime for your specific application and use the information about your domain to make the best execution model possible. This last option is preferable from almost every point of view except productivity. It's going to take a lot of developer hours to construct a runtime. It's difficult to maintain and even more difficult to modify after the fact. However, companies do pay this price because the results are generally worth it. That's why we're working on K3. We want a language in which you can construct your runtime and do so by expressing your algorithms flexibly and specifying your domain-specific information in a high-level representation so that you can let K3 choose the low-level implementation decisions that are best for your domain. We'd also like it to be able to recognize the patterns of existing runtimes, like MapReduce, and use them if they're applicable. For the case of long-running programs, we'd also like it to be able to revisit implementation decisions over time and make better decisions using execution data gathered. These are a couple of a few applications that currently do use or intend to use K3 to build their own runtime. DB Toaster is a recursive SQL compiler. Dyna is a language for weighted logic programming. And Blog is a language for specifying probabilistic graphical models. Note that all of these are declarative languages which focus on a specific class of programs. They therefore have the flexibility to choose from a large number of execution strategies and the domain-specific information to make good choices about them. So that's the problem that we want K3 to be able to solve. Let's look at some of the language design issues that we have to make decisions about, hopefully to accomplish some of these goals. So in order to express application logic, we've decided to use a trigger as the smallest unit of computation. So a trigger is a function which accepts arguments and has access to a per process state. It can perform side-effecting operations on these arguments and the state, and is written in a functional style similar to ML. It does not return a value, so it can be executed asynchronously without the call or blocking. It doesn't contain any cyclic control flow. That is, we restrict it to not have higher order functions or recursion in the body of a trigger. The slightly more complex control flow is handled through message passing. The reason we've made this restriction is that in addition to acyclic control flow and bounded iteration over collections, which you can use to do most of your work, if your collections are finite, then you can guarantee termination of a single invocation of a trigger. And this is very useful when you have to schedule multiple invocations of the trigger at a time. Here we have an example of a simple trigger. It computes a single step. Even though it's named Fibonacci, it computes a single step of a Fibonacci number. It takes its arguments and determines if it's reached the end of its computation, and accordingly sends a message either to itself or to a sink with the answer it needs. As I mentioned, complex control flow is handled through message passing. Triggers are invoked in response to receiving a message, and they are called asynchronously. The trigger invocation process is governed by a scheduler, and we find that this model is flexible enough to capture most execution patterns, such as those used by existing domain-specific runtimes like Hadoop or Prego. It may be entirely possible that if you have a more complex communication strategy, you can encode the primitives of that strategy in K3 using the messaging constructs, and then expose those constructs directly rather than go directly to the messaging primitives. Collection management is how we accomplish our data model. It is based on structural recursion. That is, the core language has collection transformers which provide bounded iteration. Like I mentioned before, if you have finite collections, then these transformations provide a guarantee of termination. Obviously, it's not completely sufficient to express everything you want to express if you had only bounded iteration. So we provide the facility to write more complex transformations through annotations, which I'll discuss in the next section. We would like to have the same guarantees about user-defined transformations as we do about the built-in ones. So we have a concept of a depth-based analysis, which allows you to provide a proof of progress of any given collection transformation. This collection model is a nested collection model, and since all of them are mutable, we provide access operators to alter parts or all of the collection. The mutability model is value-based. That is, pointers in K3 behave the same way as the values they point to by default. So if you had a set of integers, then they behave to all intents and purposes as a set of pointers to those same integers. This is done to keep the mutability model simple and out of way. Individual implementations can choose how they want to provide this mutability. Of course, there will be times when you want to actually treat the pointers as pointers, and we provide semantics to that effect. Like I mentioned, if you have a nested collection model, you'll want to decide at various granularities whether you'd like to say whether parts of the collection are mutable or not. And that can be determined either at an entire collection level or sub-collections or individual elements. And lastly, and this is a lead into the next section, but if we want to specify constraints over a collection, then we want those constraints to be maintained even if the collection is modified. So the mutation operations do check the constraints and ensure that they are in fact satisfied. So integrity constraints and other type of constraints on collections are examples of domain-specific information that we want to add to our program. We want to do this so that we can specify the high-level information directly and have the optimizer translate it into low-level implementations of how the data is stored and manipulated. So in K3, the annotation model is used to encode domain-specific information. We can attach annotations to any part of a K3 program, be it types or expressions or triggers or top-level declarations. And they are kept around in the toolchain so that they can be acted upon by any phase of the generation process. There are a lot of different types of annotations, and we can categorize them in many different dimensions. Some prominent ones are data structure annotations and control annotations. Data structure annotations specify properties about a collection, such as you want this collection to be sorted, which generally means you wanted a sorted iterator to that collection. Otherwise, you may have certain constraints about how the data structure is laid out in memory. We use the term declarative data structures to refer to a data structure which is simply a specification of what type of data you want to store and the constraints you want on that collection, and then have the optimizer choose the best implementation for that data structure and the API that you'll be using. Control annotations specify properties of code. These include things like logging events on a particular data structure or profiling sections of code. In another dimension, we can think of hints and constraints as types of annotations. Hints are pieces of information that we can provide. They won't affect the correctness of the program, but they may be useful to the optimizer to generate better code. Constraints, on the other hand, are properties that we require be satisfied and maintained. They usually require the backend to generate code to make sure these constraints are satisfied when events happen. For example, if you specify a functional dependency between fields of a collection, then you require code to make sure that when the collection is modified on insert, update, and delete, that functional dependency is actually respected. Another example is uniqueness, so that you can reject duplicates. There are a lot of other ways to categorize annotations. This is just one of them, and this table is available in the paper. You could broadly think that annotations about data structures are roughly information that would be in the types of these data structures, whereas annotations about control and execution would be part of a traditional effect system. That's just one analogy we can make. Of course, no annotation model would be complete without a way to have user-defined annotations. In this talk, I'll give a closer look at data structure annotations. Here we have the set of components of a user-defined data structure annotation. Firstly, we want to specify what are the other annotations we require. So these annotations are applied to collections, and if we want to rely on functionality provided by other annotations, then those would also have to be specified on a collection. For example, if you're writing annotation using a tree structure, then you would require that a tree annotation be provided on the same collection so that you can make use of its API. You can also define other data that you'll use and store with the collection, either on a per collection database, such as an auxiliary data structure, or as schema extensions, which are essentially per element data that we add to each element of the collection. Given that you've declared data structures, you want to have methods that you can use to operate over this data to access it. Methods are also functions. They are written in K3. They're not subject to the same restrictions as triggers, so you can write arbitrary code in them, either using higher order functions or recursion. But if you want the same guarantees as you get inside triggers, namely that they do terminate if the collection is finite, then you can use our concept of depth analysis, which allows you to give a proof that that method actually does terminate and makes progress. But these are methods that you can define on your own. If you want to modify the behavior of other methods, such as those provided by the annotations that you specified that you require, you can add books to them. This is usually in order to maintain your own data structures in response to events that occur elsewhere. This is in the vein of aspect-oriented programming. For example, you can attach post hooks to an insert method of an existing API that allows you to perform maintenance on your own data structures. And we'll take a look at this on the next slide. Here we have a simple data structure annotation, which is an index. Namely, we have a collection. It has arbitrary structure. What we do know is that we want to be able to look up elements of this collection by a particular key. We can then write an annotation, which is a set of data structure declarations and code to access them, independently of the original collection, that allows you to attach a lookup data structure and the corresponding access methods. So running through the points here, we don't need any other annotations. We do, however, need to be able to define the auxiliary lookup structure. We don't have any per element data, but we have the lookup method, which is specific to this particular index. Finally, since the original collection is mutable, we will need to be able to say how the lookup data structure is modified when the original collection is modified. And we do this by hooking into the mutation operations of the original collection. So with the knowledge of how to construct an individual annotation, let's look at how we might compose multiple annotations to produce a complex data structure like a B plus tree. So a B plus tree we can think of as a collection of blocks of elements. Here it's a nested collection model, and the T is a placeholder for whatever type of key we want to use, in this case integer. We then want to add the tree linkage to it. So the tree annotation, again, the code for the tree implementation is not here. But what it essentially does is extend each element of the outer collection, which itself is a collection, with pointers that we can use to designate its children. It can then provide access API for those children pointers, so we can use them as we would a normal tree. And note that this functionality can be provided independently of what the original type of the collection was. We don't need to know what it is in order to be able to say things about its children. We then have the numerous behaviors of the B+ tree to account for, namely the overflow and underflow handling behavior, which is coupled with a concept of maximum capacity and minimum fill. Here, these annotations are parameterized by the sizes we want to use for the B+ tree, and the custom overflow and underflow handling behaviors are specified in these two annotations. Now, these two can be done relatively independently of the data structure itself, because we don't care about what exactly is stored in those blocks, simply that there are collections that are there. Finally, this collection so far has had a block level API. That is, it's still a collection of collections, but most people want to interact with the B+ tree at an element level and have the corresponding behaviors invoked at that time. So we can write an individual BP tree annotation which provides a translation between the element level APIs that we want to use and the block level APIs that are provided by the other annotations. Note that we haven't composed all these annotations just so that we can have a single annotation which seems to do all the work itself. This annotation does simply translate our element level APIs to the block level APIs that are already there. Having B+ tree implementation in hand, we can go ahead with extending it with other behaviors. And again, these behaviors can be implemented independently of the data structure we're trying to attach them to. For example, if we have knowledge about particular layouts of the individual blocks of the B+ tree, such as a fractal layout, we can attach such an annotation to the B+ tree and have it use that layout strategy. Alternatively, we can use an annotation which logs events on this data structure and uses them to manage concurrency. With that, I'll close with the details about where we are now and where we want to go. So what we currently have is a functional core language with value-based mutation. We have a simple distributed execution model where we can run the same K3 programs on multiple machines and have them interact with each other. We can do this because each K3 program has a per-process state which is isolated from the others. We also have, as you saw, an initial model of data structure and control annotations. What are our next steps? Well, from a language point of view, we want to be able to develop an effect system which we can use to guide decisions about parallelism. We also want to expand on our method of depth analysis, which lets you write your own user-defined transforms with a guarantee of termination. From a scalability point of view, we have the K3 optimizer model to work on, as well as the ability to use our currently single process primitives to build data structures that are distributed and eventually consistent. If we develop these primitives, we can then use these directly rather than handle per process state. And that's the end of my talk. Thank you for listening, and I'll be happy to take questions.
Thank you very much. So thanks. Any feedback for Shyam or questions? You mentioned the message passing nature of K3 and the scheduler, that's a generic scheduler that you implement it, or do people have to provide their own specific schedulers to implement a particular behavior of the runtime?
There are built-in schedulers that you can use, but you can also write schedulers in K3 that you can then attach to the K3 runtime itself and use that to perform your scheduling. So you can customize it and perform dispatch based on priority of your messages, because messages can be either between triggers or from external sources. So you might want to prioritize external messages higher than your own internal messages. And this is, for example, one way of limiting recursion is that because recursion is implemented through self-message passing,
Yes.
you might want to have your scheduler scale back on self-messages to prevent runaway recursion.
Yeah.
So that's one possibility of user-defined scheduler.
Okay. So how much do you actually bootstrap K3 in K3, or this is use? How much of K3 is actually implemented in K3 already? So.
Currently none.
Okay.
But it would be nice to be able to build K3's own runtime in K3.
Okay. Okay, so I think that. Oh, James, sorry.
Sorry if this was explained and I missed it. So if you have references, pointers, it seems like you could run into sort of, if there are sneaky ways of using pointers to implement recursion, via backcaching, then you could wind up with, with non-termination anyway. So have you thought about how I guess specifically if you want to ensure that things terminate, how can you analyze things to make sure that you can't do that, and more generally, how to avoid the types of problems that you can get with aliasing when you have references?
That is an issue. We're using a limited form of references, that is, we're separating the references that can have cycles in them from references that can't. So generally, if you have the main place where you can run into problems like this are where you have references to elements that are in collections, and then have more references that point back. So this we generally limit through the type system itself. That is a reference will carry around with it the information about who has a pointer to it, so that it can reject if it's cyclic. Yes, it is expensive to maintain such pointers, but generally the operations in which you want to use such pointers are generally limited in scope, so aliases generally don't last that long.
Yeah.
But yes, that problem does exist, and the answer is to have external information to manage all of that.
Okay.